Hello, everybody. My name is Andrey Matsko, and I'll present a summary of, I would say, recent, maybe 2 years of work performed at OEwaves. And this work is related to previous presentation, and it will complement it. We basically work on usage of Kerr frequency comps announced by Kerry and introduced, and we use it for generation of low noise or high spectral purities microwaves. So this work is accomplished at OEwaves, and you can see the whole list of people who contributed to it. And let me proceed to contents. So what I will do here, I'll describe a little bit of history of RF photonic oscillator based on Kerr comp. And then I describe performance that we achieved to date, and mention how we try to get turnkey operation in the device, because device, as you will see, is already a decade old, and now from the stage of a study of fundamental physics, we're moving to making real oscillators that can work outside of laboratory. So after that, I'll describe a couple of interesting topics related to science. One of them is related to mode anti-crossing and kind of influence of high spectral density of the resonators that we have on spectral purity of the comps. And then finally, mention how it's possible to overcome a problem with inefficiency, especially power inefficiency of frequency comp oscillators that we face when we want to generate octave spanning comp and make self-locked device. And more details of some of this kind of later subject will be mentioned in the afternoon today. So just a brief introduction, I'll still make it related to generation of Kerr frequency comp. So you can see that we work with very simple system, and this system can be generated in acoustics or microwaves or in optics. And I believe that initial measurements and related phenomena that I'll describe here were observed in microwaves. So we have nonlinear cavity that has kind of crystalline linearity and continuous wave laser. So this is the whole system. So we just pump the cavity with continuous wave light, and at some power level, system starts oscillating. So if we kind of look at example of 3 modes here, if we just pump central mode to this plot, what happens that due to cross and self-phase modulation, when we put enough power in the system, the modes become equidistant, and it becomes kind of initiation point for generation of sidebands in adjustment mode to the pump mode. So at the bottom of the figure, kind of the slide, you can see basic description of the process. Usually it is called like a hyperparametric oscillation in contrast to conventional parametric oscillation, in the sense that we have 2 photons that we put to central mode here, and those 2 photons decompose into sidebands. So it's just 4-way mixing process in essence. And if you recall, Kerry mentioned that this process generates frequency comp. It is similar to conventional comp oscillators, but there is significant salient difference here. One of comp T's here, or one of comp harmonics, is a pump laser. So if our pump laser is stable enough, we don't need to lock 2 points of this comp oscillator. It's fundamentally important. We just need to lock only either repetition rate or another harmonic, because one of the T's is already fixed. It is parametric process, it's not a laser. So let me go to next slide. This is what was observed recently, starting I think in 2014 demonstration by Tobias Kippenberg at EPFL, that if we pump resonator strongly enough, we can get broad frequency comps that corresponds to a train of optical pulses. And importantly, that kind of depending on configuration of our cavity, we can observe either dark pulses or bright pulses in the system. So within the resonator, we can generate a pulse. So kind of at some optimum condition, instead of kind of all harmonics become mode locked, and inside the cavity, pulse is excited. But what is interesting here is that if we use drop configuration, we will see a bright pulse. But if we have kind of just configuration for kind of just a couple, add configuration for the coupler, we observe a dark pulse there. Usually people don't look at dark pulses, they just remove the carrier and look for bright pulses. However, dark pulses are there still. And as I mentioned in in the presentations, that we are interested in generation of radio frequency signals produced by this frequency comp on fast photodiodes. This is corresponds to what Kerry discussed with brilliant lasers. And with this perspective, we don't care much if we have a pulse in the system or don't. We're interested in spectral purity of RF signal. And as you will see, it is not necessary to have a short pulse there. It is possible to have just phase lock number of modes that are not, that don't correspond to soliton traveling within the cavity. So to explain the physics of the system, let me go again to this 3-mode example. So if we consider just single mode pumped optically, what happens? We just put light there, and at some point we observe bistability. And this bistable curve is shown by blue line on each of those plots on top panels. And red dashed branch is unstable. However, if we take into account 2 side bands, suddenly we see that instead of only 2 stable branches, we may observe another stable branch, which is shown by green line here. And this stable branch corresponds to oscillation. And this is exactly what we use in our oscillator. And depending on dispersion in the system, and dispersion is responsible to splitting, frequency splitting between the pump mode and adjacent modes, we can have different conditions for oscillations. And it is possible to show that actually at any condition but 0 dispersion, when initially all modes are equidistant, we can observe stable oscillation. And this is actually interesting because it looks like that it's better to have all modes equidistant from the beginning to have generation of equidistant spectrum, but it is not the case. So whatever at 0 dispersion, system becomes not very stable. Actually, at 0 dispersion, higher order, at 0 second order dispersion, higher order dispersion terms take place, and as I'll show at the end of the presentation, they become very important. So just a couple of timeline points. So the first demonstration of microresonator-based devices was done at GPL and Caltech nearly simultaneously. At Caltech, it was achieved with optical sideband generation. In the Jet Propulsion Laboratory, it was shown that pumping calcium fluoride resonator with continuous wave light, it is possible to get spectrally pure RF signal. And optical spectrum wasn't initially observed. It was just artifact. We just pumped resonator and we observed spectrally pure RF signal. Then in 2007, Tobias Kippenberg at the PFL, I think it was still Germany, it was Max Planck. What he did, he just pumped a few silica resonator hard enough and he observed generation of spectrally pure comp. And the most important observation in this paper is that he proven very accurately that this comp is equidistant. Because it's not obvious, okay, there are many harmonics, but it can be chaotic. No, it was equidistant. Then, nearly the same time, at OEwaves, we just used another resonator, and it was calcium fluoride. We pumped it hard enough, and we observed comp with low enough repetition rate, and shown that it is possible to improve spectral purity just by increasing optical pump power and increasing quality factor of the resonator. So, next step, we shown that that's what I mentioned, that it is possible to just stabilize the laser that pumps the resonator and have a feedback to the resonator, to stabilize the resonator temperature, to stabilize the whole comp, and basically to have low noise and low variation of its frequency over time. Another direction in the development of the application of the microcomps was generation of pulses. So initially, nobody was able to generate mode-locked pulses within the resonator. So what people did, and I think it was done at Purdue University, just use several harmonics of the microcomp and adjust phases optimally of each harmonic to generate short pulses. Interestingly enough, that particular realization of the frequency comp didn't have a repeatable frequency difference between harmonics. So kind of each time it required specific phase selection for each harmonic to get a short pulse. Kind of broad combs were generated after that, and it was shown that it is possible to get, again, using similar technique, very short optical pulses. And finally, a couple of years ago, at the PFL, it was demonstrated experimentally that it is possible to get short pulses just within the cavity by itself, without any adjustment, any change of the phase of the harmonic of the light that leaves the resonator. There are a lot of different dynamic states of this comb oscillator. So it is not kind of a very simple structure if we wanted to make a device, because kind of our goal to make a device here. So we need to look and see what can we observe in the cavity. And this slide demonstrates possible solutions and dynamic states that were demonstrated both theoretically and experimentally. So definitely there are two phase stable regimes. One of them corresponds to generation of optical pulses, and the other corresponds to generation of kind of, I would say, modulation instability signals that are still stable. Breathers corresponding to changing of the bandwidth of the comb and pulse duration possible as well. Finally, there are many possible stable solutions in the system. So it's not kind of single branch or single attractor that can be achieved. In fact, in every resonator, for every selection of a pump and frequency, when frequency comb occurs in the cavity, there are many solutions, and it is possible to show that each of the solutions corresponds to 1, 2, 3, and many pulses kind of traveling within the resonator at the same time. Finally, a huge region of the dynamic range of this oscillator corresponds to chaotic generation of frequency combs. And I would say that early demonstration, especially with broad frequency combs, were chaotic. Interestingly enough, if you look at optical spectrum analyzers that average a signal over time, those combs look pretty nice, but it happens because spectrum analyzer, both radio frequency and optical, averages down the signal. So it is not necessarily possible to see that actually all those harmonics fluctuate in frequency and in power. So at OEwaves, we tried to integrate frequency combs starting, I would say, 2010. The first presentation on integrated devices were done here at IFCS in 2010. And we made different prototypes, but the most advanced comb generator now is in K band, and the size of this generator is less than a sugar cube, and I would say that it's pretty mature, and now it's kind of undergoing different tests, and technology readiness level of this device is already, I would say, 8 or even approaching 9, since I think that OEwaves produces it like commercially. Those oscillators, though, don't use mode-locked regime of frequency combs. And as I'll show in next couple of slides, mode-locked regime is the best one to generate spectrally pure signals at low offset frequencies. So this is kind of how mode-locked comb spectrum looks like. So green lines here show a couple of envelopes of frequency combs in microresonator as outside at the output. And top figure shows basically spectrum of a single soliton traveling within the cavity, and we can say single soliton by numerical simulation, since we didn't make optical observation. And this bottom figure shows green line shows a couple of soliton comb generated in the same cavity. And on the left-hand side, you can see how we observe different comb regimes. We kind of look at a Lie curve of our laser, which is injection locked, self-injection locked to the cavity, and we see different steps. So in the region 1, we have no comb. Then at region 2, we have chaotic generation of oscillation, and then finally you see multiple steps that correspond to different power level of the laser, and those correspond to different regimes of the combs that have different pulse number and sometimes kind of slightly different repetition rate because of complexity of the spectrum of the cavity. So this is how RF signal looks like, and we have a couple of spurious lines, usually due to 60 Hz signals. And on the bottom, you can see the structure of packaged devices we kind of tend to make. So we have a laser, and it is mounted on substrate, and this laser is self-injection locked to the cavity. And basically, self-injection locking occurs because of some residual scattering within the cavity. So this cavity has quality factor around 10 to the 8, 10 to the loaded 10 to the 8, but unloaded is 10 to the 10. And due to scattering back to the laser, we have laser frequency locked to the resonator, and it allows to kind of pump it very efficiently, and it reduces laser noise. And as I mentioned again, in this frequency comp, laser represents one of harmonic of the comp. So we want to have laser with extremely low phase noise to get good comp oscillator. And we have evanescent prism coupler. So at next session, you'll see some kind of first results where we achieved good coupling with planar waveguides that would allow to kind of integration of these resonators much more efficiently into optical platforms. And this kind of structure can be very small. You can see that the laser by itself is a couple of millimeter in size, and the resonators usually don't exceed 5 millimeter in diameter and 100 micron thickness. And the whole structure can be packaged pretty tight. And power consumption is usually very small, since kind of in our conventional devices that generate spectrally pure radio RF signals, power from the laser is less than 10 milliwatt. So this is one of the best curves that we achieved, I would say, nearly a year ago, and we kind of still making oscillators approximately with the same performance and trying to improve this performance kind of by adjusting some, kind of removing some technical issues. So let me just describe what you observe here. So curve 1 corresponds to phase noise produced by mode-locked Kerr frequency component fast photodetector. It's 10 gigahertz carrier. Blue curve, curve 2, it was just the same frequency comp, but we took RF signal and sent it through RF filter. And RF filter just strip off high noise because of short noise at high frequencies, and allowed to basically put it to KT level. And because of this, you can see that the floor decreased. Now we look at curve 4, it is fundamental short noise that limits comp spectral purity. It's kind of like, I'll explain where it comes from in the next slides. Curve 3 corresponds to fundamental thermodynamic noise in the system. And thermodynamic noise comes because we have small size of the cavity and don't kind of reduce the temperature to kind of cryogenic level. So at that temperature, instabilities of radius of the resonator and index of refraction of the resonator result in instability of the repetition rate of this comp oscillator. And finally, curve 5 is our current sensitivity of our current phase noise measurement system. You can see that it kind of approaches this result. I think we can improve this result approximately by 10 dB when we beat two oscillators together. But still, this curve represents one of basic achievements with the oscillator. Now, if we look at Allen deviation of this system, we can see that at approximately it reaches 10 to the minus 11 at 1 second and then drifts up because it's free running oscillator and it needs locking to achieve good stability. Recently, we got Allen deviation of the order of 6 to the minus 12 at 1 second, which is good, but kind of pushing it down is a hard task, and we're trying to improve it in both ways. Just push 1 second down and then lock the system to atomic lines. What is interesting is that we observe that even to measure this kind of performance of the oscillator, we cannot use conventional rubidium clocks that we use like local oscillator in the system, because a rubidium clock has pretty bad oscillator itself. So even if you look at synthesizer noise at short term, it is better to use synthesizers than rubidium clock. And we nearly at the limit of sensitivity of Allen deviation measurement with this technique. So now it's interesting to mention noise sources of the device. So if we speak about quantum noise, what is interesting, it just kind of, okay, what has happened? Did I push anything? Mm-hmm. Well, the thing doesn't go away, and I don't know how to remove it. Does anybody knows how to take this thing away? Anyway, I'll continue, and maybe Scott helps to remove it. Escape. Okay. Good. Thank you. Thanks. Okay, so if we speak about quantum noise, it is kind of quite general feature related to all micro-resonator devices. For instance, I think that Kerr showed it for Brilliant laser, and I think we shown it for micro optoelectronic oscillator based on a nonlinear whispering gallery mode lithium niobate resonators. It's kind of, it has nonlinearity, and nonlinearity of the system that corresponds to kind of nonlinearity of the material and depends on mode volume, limit the stability of the system. Because we have kind of two effects. One of them is conventional Charlotte limit, and the other is broadening of the system, like self-broadening due to power in the system. And it's interesting that we have a limiting factor for the maximum Allen deviation in the system that kind of is given only by those two factors. It's nonlinearity, mode volume, and basically repetition rate here. And repetition rate by itself depends on volume. As you can understand, that decreasing size, we increasing repetition rate. So from this perspective, we wanted to increase the volume to increase fundamental stability. So now to look and to see where we are now, I just put here kind of a couple of materials, kind of several examples, and Allen deviation at 1 second on the right column in this table. And you can see that it kind of easily reaches 10 to the minus 15 at 1 second. So we are far from this point, since we just kind of on the order of 16 to the minus 12 at best. So we have plenty of room for improvement here. Next is thermodynamic noise, and this noise again depends on volume of the mode and volume of the resonator. It's proportional to temperature squared, and this noise still is small. I shown picture before that we still have, like, in phase noise scale we have like 30 dB room for improvement. So the basic limitation here comes from technical noises, and this is what we try to handle right now. So we have thermal noise of resonator, but this noise kind of, it is nearly, kind of, it is close to fundamental noise, but it comes from leakage of noise from the environment. We have transfer of laser noise that kind of looks like the basic reason for this phase noise hump, though it is not still clear where it comes from. And finally, we have short noise limit in the system. We're trying to kind of handle all of them and use better laser to improve this performance. So, as I mentioned, to have a better laser, we use self-rejection locking technique, and because of back reflection, back scattering to the resonator, we don't have any isolator between of the laser and the resonator. We have line shrink, and laser reaches pretty good level of frequency noise, as you can see on the left top panel, but it's kind of still like, I would say, 50 dB away from LIGA spectral purity, but it still looks pretty good. So, just I have 5 minutes left, and I think I just kind of in the middle of my presentation, so I'll limit it by kind of a couple of interesting observations that we kind of made recently. So first of all, as I mentioned, that initially we used to work with very narrow frequency comps and generate properly, kind of proper RF signals. But then after observing mode-locked comp, we decided, okay, mode-locked comp definitely have much better low frequency phase noise. However, kind of from build to build, because of high density spectrum in the resonator, we observe some comps that I would say look ugly, like this red one. It has many lines, and it is completely kind of, it definitely doesn't produce signals corresponding to pulses within the cavity. But if you look at phase noise picture, you can see that, well, at small offsets, small frequencies from the carrier, phase noise is not so good. It is worse than mode-locked regime, but at higher offsets it is better. And frankly speaking, it is not very clear why. But this is interesting that still it is kind of, it is possible to kind of to play with the system, and sometimes observation shows better results. So in our kind of commercial units, we try to get comms that are reliable and maybe not kind of don't performing like with extremely good phase noise, but repeatable. So this is another observation when narrow comms perform well enough. It's kind of, we for instance can get minus 157 dBc per Hertz floor, pumping less than 5 milliwatt in the cavity. So in the next few slides I'll just show what was kind of announced, what we're trying to do in the system. So we're trying to make oscillators that self-starts, and that can be kind of, you know, push button, type of oscillator that doesn't require a PhD standing aside of it. So if you look on performance of the free-running device, we can see that if we just put laser into proper position, proper detuning, proper power, we can see that there are many regimes. The system runs for several hours and it jumps to another regime with slightly different radio frequency. And it keeps jumping, and finally it jumps out of the locking range. So first of all, we need locking, and secondly, we need efficient turnkey operation just to start the device. And we did it using simple lab view technique right now, and I would say it works pretty robustly. We don't need anybody to start it. We kind of switch on the device, and the system by feedback to the laser and by measuring the DC signal or Li curve and radio frequency signal power, we can make it work, and it works for instance for a day. But this system has a disadvantage. Still, we need to find the most the most optimum position to generate spectral purity, high spectral purity signals there. And this is the next kind of stage where we what we're working on. And I think I will not kind of I'll just show some problems and will end at this point. This is a basic problem we faced right now. And on the bottom of this slide, you can see curves of the comp spectra we wanted to observe. And on the top, you can see that we usually observe, unless we do some specific preparation and engineering resonator shape. And you can see that there are many dips in the comp spectra, and those dips occur because of interaction between among mode families within the same cavity. Those interactions result in deterioration of dispersion, Broad velocity dispersion. So it's not kind of theory, doesn't do much here, because it was shown by EPFL. They measured this dispersion within the cavity, that in fact kind of usual real resonator cannot be explained just by one mode family, and kind of it is very hard in fact to make a resonator that produces single pulse within the cavity. And if you want to make a device, we need to solve this problem, and I think we kind of on the road doing it, and kind of we have very good perspective with respect to the solution. And at this point I'll end. Thank you.